Hi, welcome everybody. All right. Um, Thank you so much for coming tonight. I think other people will be coming in through the door. I know we had a very long list of RSVPs, but I'm Carol Willis. I'm the founder, director, and curator of the Skyscraper Museum. And we're really delighted to be here at SOM tonight for I think it's the fifth in the series of our Tall Timber lecture series, our semester of timber. This evening, though, Tall Timber, Upfront Carbon, the Now narrative brings together two of the great experts and academics who have investigated in their research and then spoken at myriad conferences and taught hundreds of students and organized academic conferences on mass timber and beyond that on all kinds of biogenic materials with low carbon footprints. And I'm not the person to talk about this. The order of the presentations are going to be Alan Organsky and then David Lewis. So I will introduce them, and there'll be a moderated conversation, which was going to be here in person with Fred Bernstein, a journalist who has covered mass timber and embodied energy, which is really his thing at the moment, a kind of obsession with Fred. But Fred came down with COVID last night. And so he is going to be here as a big head on the screen, and we hope all the technology is going to work out just fine. But I'm going to introduce Ted a little bit more when he comes onto the screen, and in our post-production, all of these things will be smoothed out. So the first of our speakers that I want to profile a little bit is Alan Organsky, who is the founding an architect and the founding principal with Lisa Gray of Gray Organsky Architects. He is also a professor at Yale School of Architecture, where he's taught for about two decades. He's been off for the last couple of years since actually 2021, where he was appointed the director of the Innovations Lab at the Bauhaus Earth, a Berlin-based interdisciplinary initiative. And there are all kinds of studies and research that undergo all around the ideas of biogenic materials and anthropogenic and environmental impacts. And I should get off the stage very quickly here and hand it over because he has an absolutely spectacular presentation in order to explain the ideas of embodied carbon and the distinction between operational carbon. Our second presenter is David Lewis, and is New York based, and so many of you know him. He is one of the founding principals of Lewis Cermaki Lewis Architects. He has for many years, but is just concluding a long tenure as the dean at Parsons New School as in the Department of Constructed Environments. And part of the reason that Alan and David have been brought together this evening is because I asked, they're represented in the exhibition, and I asked them in particular to talk about the role of education in their very early researches and then publications, but especially the academic conferences that were held at the New School on timber in the city, about 3, I think, conferences that brought together many of the same speakers that we have in our series. And also, Alan at Yale headed a research project called Timber City that produced a publication in which Andrew Waugh was represented and Andrew Bernheimer was the editor of. And the two Andrews will be together next week at the Skyscraper Museum in order to talk about that. So I'm really interested as a curator and a historian in this short history, which is comprehensible. It's a tellable tale of the embrace, the kind of invention and embrace of mass timber in North America, in part taken over from the European context, but also a function of the regionalism, especially I think in the Pacific Northwest. But also in what happened on the East Coast is this research investigations that come to these larger questions of the relationship of and the responsibility of the architectural community and the built environment, and projecting what is the future of the interaction of climate change and our overall crisis and our complicity within that. So these academic projects have been enormously important, I thought, and wanted to include in the exhibition as one aspect or one leg of the stool of the research about how the mass timber community comes together and how they spread the word. So I think they're going to do that a little bit in their presentations, although architects always want to talk about their current work. And last part of this title about upfront carbon, which is embodied carbon, and the now narrative, because one thing that I observed in trying to put together the story of the short decade of the history of mass timber in North America is that when you line these buildings up chronologically, and when you think about the bigger ideas and their trajectory, but also their dates and the chronology of them, what has happened in the world that I observe of engineers and architects, what I observe is when I'm sitting in the audience listening to people present their work, is that what used to be the overarching narrative or kind of heightening awareness of operational carbon has switched to embodied carbon. And the discussion now, conference I was in Singapore back last October, the engineers, whether they were structural, MEP, environmental engineers, only talked about embodied carbon. They said operational carbon is over. This is the only issue that we should be discussing. And you're going to hear the same thing from our speakers tonight. So that's the now narrative. And so the parallel trajectory and until they get into a kind of concurrent wave of working together, the awareness of the importance of embodied carbon, this upfront carbon, the mortgage of carbon in everything that we do. And the moment, which is now that we realize we have no time, that is the now narrative. And so that was a lot of the thesis of how all of this came together. And I've spoken in Zooms and everything with Alan and David and also his brother Paul. And I know that they're going to tell us all of the details in order to support my conclusion, which is how I came to my understanding of this in the first place through their work. So Alan, please take over.
Thanks, Carol, and for your curation of this series of talks and the show at the Skyscraper Museum. And thanks to Daniel and Shi for doing all this setup, and to SOM for hosting, and to friends I see in the audience, new and old, who are here. Today, I want to talk about a lot of things because it's in my brain and it relates to all the things that Carol's raised. And I'm going to try not to move around too much so I can stay on Zoom for everybody out there. Really, I'm talking today about architecture and not buildings per se, but rather architecture as a means to conceive and implement building. And that's where it all starts. And so architecture has many forms and many shapes. We could talk about the architecture of wood. I'm not going to talk that much about it, but this amazing woodcut of an ash tree from Brian Nash Gill tells us a lot about two things. One, the sort of biophilic response we have to this natural material. You know, we read the age of the tree, we read the disturbance in the forest as a kind of history, the flaws that we all experience. I just had knee surgery, so I'm feeling very, very, very akin to the broken knots and things like that in the tree. But also in this, we can read all of the reasons why wood historically has been left behind by 20th century engineers and architects because of the flaws and the lack of predictability and uniformity. So I won't really talk too much about that architecture. And I'm going to talk a little bit about my architecture because of Carol notes, you know, we're always like trying to sell ourselves a bit. But you know, building architecture is something that is a vehicle for some of these ideas, an important one. What the architecture I would really like to talk about today is the architecture of the system that produces buildings and a host of environmental impacts throughout the building life cycle, from the extraction of materials from the Earth's surface or deep in its lithosphere to the disposal of a building at the end of its service life and what happens to that material and all the energy that went into it, the so-called embodied aspects of building. But first, I think I want to frame this question. This is Tokyo. Tokyo, as you know, is the largest population of any metropolitan area in the world, 39, I think, million people. But an industrial ecologist will tell you that it's also the largest stockpile of human-made material in the world, which is an amazing thing to think about, because with the making of this thing, this giant city, comes a host of impacts that we really haven't thought too much about. And carbon emissions is one of them, but we can trace it from the beginning to the conversion of land and ecosystems to non-biomass surfaces, impervious surfaces, all the way down. If we looked at some of the chips or some of the materials going into some of the control systems in our buildings, potentially human exploitation, possibly even child labor and exploitation. So if you think about that, and you think about 2.5 billion people in the next 25 years that will be occupying global cities, which represents a factor of land increase of three times the land area if we continue to build with the morphologies that we're currently building with, low suburban sprawl, which is about the size of 2 New Yorks. Again, I'm not talking about a city the size of New York State. I'm talking about a building the size of New York State, or 2 Irelands for the Europeans in the crowd, or for our Asian colleagues, it's 4 Bhutans. So just imagine that kind of coverage and quantity, which is really great news for the construction industry, $97 trillion worth of value. We should be happy about that, but we could do it terribly wrong. And in the process, we know now that 42% of all emissions coming out of building sector activity is a number of that all building sector activity produces 42% of anthropogenic emissions. And by the way, that number has been climbing as we assess all of the various sort of levers in the system that create that. And I'll get a little more into this, half of which will be associated with embodied emissions by 2050 from the architects 2030, which is an emission of carbon dioxide alone, not to talk about other impacts, of 71 gigatons of carbon, right? And that will blow us through all of the possible guardrails that we've imagined for ourselves in terms of carbon impact reductions. So this is a story about 2 landscapes, the forest and its relationship historically since the agricultural revolution to the growing cities that are human settlement. And if we really think about Tokyo and all of that material, we can note that 2020 was a kind of red letter year. It was the point at which anthropogenic mass, all the products of the technosphere, now outweigh the Earth's biomass. So that's a pretty important point. And we're also creating, when we dig this material out of the earth or scrape it off the surface, we're producing a lot of emissions. And that's kind of what I want to talk about. But emissions are really a proxy for a lot of different kinds of impacts. So that number I talked about, which comes from a study by Architecture 2030, is that by 2050, 49% of building sector emissions will be associated with the embodied phase. Talk about what that is exactly. All the stuff that goes on in building that's not operational energy consumption. And here's one of those impacts that's created by that. So across the building life cycle, 23% of all the emissions that we produce in the world are associated with the things that we specify, the materials that we specify in our buildings. Raw material extraction, material handling and transport, processing and manufacture. This is from David Plowden's amazing photo essay on the Bethlehem steel production in the 60s. During the construction itself, and then renovation and repair, and then finally the demolition and disposal. These are all the kinds of forces of the so-called embodied emissions of carbon. Just lost one screen, it's back. So these are the operational emissions. The minute we open the doors and turn on the lights, the first time we use the building, what we see is a sort of slow emission of carbon. Even in the lowest so-called net zero energy buildings, we're going to have some emissions. The problem is, as Carol pointed out, is that at the beginning, there's a carbon spike when we actually build the thing. We extract resources and transport them and process them. And then it flattens for a while, embodied emissions, and then the building needs to be repaired and serviced, and those emissions occur again. And then at the end of life, of course, there's another sort of burst of emissions because of the demolition and disassembly processes that go into the building. And so in a way, we can be really efficient about operational emissions, but we'll never catch up with the debt we owe the environment through this embodied phase. So we're pretty familiar with this diagram from the IPCC. We're charging toward our 1.5 degree guardrail. And if we keep building and doing all the activities that we currently do, we're going to blow through in a sort of business as usual scenario, and the Earth will be relatively difficult place to live by 2100, not too long. Of course, we talk a lot about decarbonizing different sectors, and that will flatten that curve out, but we're still going to overshoot. And so the question is, how do we produce negative emissions? How do we use, say, a lever like the building sector and building activity to reverse this trend? So the first thing is we need to really understand carbon literacy. And I wrote this book with a couple of colleagues. I hope somebody's read it, or at least someone was willing to buy it. But it really tracks the sort of question of where is carbon lodged in the Earth, both in the things that existed naturally in the Earth and also in the future use of it, of the carbon-laden materials in building. And this brought us to a real question that we've been exploring through building. Again, I'm going to get a little into my practice, this idea of carbon as a kind of currency, where it's no longer dollars, renminbi, or euros, but rather the flow of carbon is actually an exchange that is a really important aspect of how we conduct our work. And so we built a school in New Haven for some inner city kids at a public charter school, entirely out of CLT and bio-based materials. We learned a lot in the process about the capacity of industry to prefabricate flat pack components. We got great feedback from the kids in the school. They said the building smelled good, which I think is a pretty good criteria for design. Egress systems were made out of timber rather than steel pan stairs. And in the end, the school was a pretty successful place, serving 20,000 people coming through the New Haven Ecology Project, along with the 250 high school kids who work there. And I won't go into that too much, except to say that really the way we think of buildings as in systems, that's how we specify components. But when you look at it rather than as form, but rather as a set of impacts, and you start to see where emissions occur in the things that we specify, and then actually consider where is their capacity to store carbon using this natural photosynthetic process of forest growth, we start to really understand how buildings can start to be agents in the reversal of climate change. And so with this student, young guy, we did a study of how much carbon was lodged inside this building based on the bio-based materials. And we found that it was essentially about 100 cars worth of annual emissions offset by the carbon that was stored in the wood of this building, which is, I think, an important insight. And if you start to scale up, you imagine how that goes. And so for just a kind of comparison's sake, we often talk about the comparative weight, the carbon dioxide emissions per weight of material. But if you take into account the relative strength or the strength to weight ratio of these materials, you start to see that wood will get you 4 times as much value, plus has lower emissions. And so we start to really see great benefits in terms of emissions reductions in the use of wood when it's done properly from regeneratively managed forests, of course. But the storage piece is a really important thing that became part of our Timber City research initiative, which is that unlike mostly concrete and not at all steel, we can actually store wood in these kinds of structures for as long as they're protected. And it's kind of amazing that chemical adhesives, combined with a technology called finger joining, which is about 100 years old, we can take little sticks of wood, higher yields from forests that are managed, smaller trees that are being cut, and we can produce really big cross sections. And what's more, we can distribute the different lamella or layers within that based on their capacity to have structural resistance. So the really good fiber, the high-grade fiber, gets moved to the tensile and compression edges of a beam, let's say, and the cheaper stuff gets lodged in the middle. So now we're actually truly making a better beam, and we've known how to do this as long as glulam has been made. And of course, we also know that it's very amenable to digital fabrication systems. And we even know that we can start to substitute different species that are underutilized, like beechwood, in this case of this beechwood dowel joinery for a 5-story building produced by Bloomer Lehmann in Switzerland. We can start to actually choose different species based on their properties from the forest and apply them to tall buildings. So think about it. It's a tectonic system where we have a bunch of sticks, and we found different ways to put them together to make pretty large components and tectonic systems of building. And then we've allowed them by building code. The IBC allows buildings with different kinds of encapsulation requirements up to 18 stories, which is 3 times what we were allowed to do with heavy timber prior to the IBC code adoption. So the question becomes, if we can do all this, is building wood skyscrapers what we should be doing? And that's kind of what I'd like to talk about today. And that's where I get to talk about my practice a little bit, which is that we've been working on mass timber for a pretty long time. This bridge we designed was made in 1996. And it was a first experiment with just the industrial techniques required because we were building the bridges ourselves and we had to figure out the logistics. And that became a series of experiments through different kinds of bridges, again, self-built, self-performed, where we were really focused on how do we move this stuff into the site? How do we put it together? How do we ensure that it's going to be durable? How do we maintain structural integrity in really slender, light systems, but are monolithic and therefore fairly weather resistant over time? And then that's turned into bigger projects working for a sort of alphabet soup of different agencies along the Hudson River, crossing the Metro-North Railway, and using a hybrid system of timber, steel, concrete, knowing full well that that is really part of the sort of transitional aspect of engaging these mass timber products. And houses have been important to us as a way to test systems of building, from the cabinet detail, laminated curved laminated wood, to exterior cladding and structural systems, how we retrofit buildings, which is such an important part of the decarbonization process, to urban buildings that were really unused and neglected, and turn them into rich, carbon rich and architecturally rich places. But also then, what does it mean to move those same materials into the city and handle that without creating a huge amount of disturbance? Or in the case with the Acme Lofts, which we worked on with Jeff Spiritos, who's here tonight, the idea that this super light, stiff material can actually reinforce an unreinforced historical masonry building, just using a shaft that's threaded down to its foundations to literally double the capacity of a historic building in terms of housing. And then the question, of course, when you start making housing is, can you make affordable housing? I'm jumping ahead, sorry. You got me under pressure, Carol, so I'm trying to move fast. This is an important piece, and I'm going to really let David talk about this, but the buildings that we make, especially for educational institutions, become test beds for both education and industry, and that's a really important piece. But it has to address not just the building itself and the cool forms and techniques that we use, but rather the entire system, as at the Anthony Timberland Center in Arkansas, where we looked at the entire material shed that could possibly serve the building and also revitalize a moribund economy in the country, in the state. And affordability, also working with Jeff Spiritos in New York and his great analysis for the US Forest Service of comparative costs of building and how to make a building entirely out of bio-based materials and make it affordable for a community much in need of housing. And this project's going to be finished shortly, and it has been a test for a lot of reasons, which I won't go into here. And then finally, at a more national scale, we're working in Thimphu in Bhutan, working with the government to try to not just make a building, but to refashion the entire supply chain based on the sustainable use of resources. And how to do that and be respectful of a very strong architectural tradition, working with regional architects, national architects, and really studying how we might create cascading products coming out of the timber, the sustainable timber industry, to really create a whole host of parts of the building assembly. And this requires us to analyze how much demand there could be in the future, and also how much capacity the forest management units in Bhutan have to produce timber, because that's a really important part of it. We have to be sustainable systemically. And so that brings me really to the kind of vision that we've tried to promote, which is that there is a synergy between these once antagonistic systems and landscapes, the city and the forest. But we can build synergies first, really by understanding regional forest differences and the different kinds of species that are coming out of them, and as stem successions follow, say, a disturbance like wind throw or a harvest, that how the wood grows and what species grow at different stages. and then how we might possibly track the carbon stored in that and potentially the biodiversity benefits that are coming out of it, and how we might then map different products of different types from the forest and this forest dynamic into both low-rise building, which we already know how to do pretty well, but more importantly, higher rise building, mid to high rise building, where we start to see real benefits of this transfer of forest carbon into these durable consumer products that we call buildings. So what we're really positing is that there exists scientifically, experientially, a metabolic, circular, and regenerative system called forests. And can we mimic that? And through really good quality building that's carefully assessed, can we also produce a metabolic, circular, and regenerative geotechnology? It's a bold move. I don't think it's going to happen necessarily. I think a lot of people are concerned about the health of forests for good reason, worried about the overconsumption of wood to build cities. We know the carbon sink globally is collapsing for a whole host of reasons. Wildfire is the most sort of journalist-friendly aspect of it, but there are a whole host of other reasons for forest loss. Agricultural conversions are raging across the Amazon, Congo, mining and mineral extraction is happening. Forest product use represents a part of it. About 20% of global forests are used for wood products. 50% of those are actually domestic fuel. So that's something to keep in mind. Suburbanization is obviously a huge force in land conversion. And finally, climate change is doing it too. And I think really what's important as we look at that, we need to understand a recent study from my colleagues at Yale and the Applied Science Synthesis program showed that if we stop cutting, the carbon sink collapses, if we leave the forest alone because of all these other forces. If we cut and see these extreme disturbances, it collapses even faster. So this is the no cut, no disturbance, which actually doesn't exist. This is no cut, extreme disturbance, which does exist. And then this is the regenerative cut, which is really the only way. The focus on existing second growth forests of restoration and management really is the only way to maintain the forest carbon sink. And so then the question about mass timber can't just be mass timber. I'm throwing a slide in about fungus right now for people who are into mycelium, because it will be a product that we'll be dealing with in the next 10 or 15 years. We got to get rid of industrial forestry. It's not the way to manage forests. Unfortunately, it's the way that we pretty much cut forests for the current mass timber products that we use. We have to think rather about what the forest can offer us on a sustainable level. And we have to think about all of the forces and the goals of forest management, habitat and biodiversity enhancement, pathogen invasive species control, carbon storage in the forest, water quality improvement, soil remediation, all of the things that foresters who are ecologically minded are thinking about, we can think about in the specifications of building components. And we need to teach our students how to go into the forest and understand that, even though they may be architects or builders. We need to carry that through the entire process of from the sourcing of that material to the making of buildings. And so we can look truly at how the forest grows, different products that are coming out of it, how long they need to grow before they're cut, when they're near the end of their life, how that mortality plays into different models of soil remediation and biodiversity enhancement, how to use the products in different novel ways, and how to map them onto buildings. And when we do that, we can start to see benefits across the system. Got to stop our extractive economies in building. We have to use circular economic means to solve buildings problems, because wood won't do it alone. We need the support of the waste flows from different sources. We need to transform them. We need to reuse them for product and make new products out of them. And yes, you know a lot about designing buildings as material banks and design for disassembly, but we have to, with that, develop scenarios for the reuse of those materials when we design, which is a kind of future-proofing of the building system as we know it and the life cycle. We have to stop tearing down buildings without really assessing what we're losing in terms of the embodied emissions that already exist and held in those things. And we have to stop land conversion by reducing sprawl and increasing what I would call convivial density. So there's so many benefits that come out of well-placed density, which doesn't always translate to height. We're really good at governing within political boundaries, but that doesn't really help us to manage resources. And so we have to think bioregionally. And we can do that by breaking the sort of stranglehold that exists between a mineral-based, fossil fuel-intensive manufacturing processes and dense convivial city building. And we can map every bioregional component onto buildings. And this will become part of the new design criteria for our students. This means rural workforce opportunity. It means indigenous enfranchisement of indigenous communities. It means urban workforce opportunity. So there's a socioeconomic, cultural component to this as well. It's a big lift. It's a confusing diagram to think about decarbonized design. But this is really how we need to function. And we need to understand the decisions we make may produce either a high emission carbon emissions building or a low one. And this is one of the questions for tall building builders. So I'll close with this carbon timeline, 350 million years of sequestration in global forests during the Carboniferous era, 150 years where a lot of it was that fossil hydrocarbon was excavated and burned, combusted for energy and for making material. So the question is, can we actually reform our practices, the Anthropocene more broadly, and try to use all of these different techniques, systemic in nature, to solve the problems? And if this is our motivation, rather than just making the tallest building, then I think tall building is the answer. Thank you very much.
Thanks, Alan. That's I'm going to try to tell a parallel story but it's critical to understand what Alan is sharing in the sort of range of approaches that come into play, because it's also one of the challenges of introducing mass timber within an educational framework. So I'm going to start by asking you to begin by thinking where you were a dozen years ago. This is pre-Taylor Swift, I think. In a short history of tall timber within education, at that time, Parsons received a grant from the BSLC, or the Binational Softwood Lumber Council, in collaboration with the ACSA, to organize a two-part event. First, a New York-based conference, Timber in the City, bringing together experts, architects, engineers, developers, and ecologists to examine how to build mass timber projects in dense urban environments to address the looming housing crisis. Sound familiar? The conference would be followed by a student competition to envision a wood mid-rise mixed-use complex with affordable units in Red Hook. My colleague, Andy Bernheimer, organized this conference and competition, gathering together Andrew Waugh, Michael Green, and Case DeJager as the speakers. The conference set up the competition, providing key information about what mass timber is for an audience that didn't really know much about it. Following the 2008 subprime housing mortgage crisis, this work was in part motivated by a desire to diversify market opportunities for softwood framing, expanding now into mass timber that had been standardized in Europe already. The competition brought together an esteemed panel of jurors, including Alan, Abby Hamlin, Tricia Stuth, and Mark Crevellier, as well as Michael Green and Andrew Waugh. The competition enticed over 1,000 students, right? One of the largest that the ACSA had seen, and generated significant interest, including introducing students and educators to systems of mass timber, mostly CLT construction, many for the first time. The competition focused on assembly systems, with winning entry embracing the prefabrication of mass customization embedded in CLT production. That's a really important thing that is also a problem. The results of the first Timber in the City were edited by Andy and published in the book of the same name, with expanded chapters to include mass timber productions from around the world. And also worth noting that the same year, 2013, SOM published their Timber Tower Research Project, which is also featured in the exhibition, the Skyscraper Museum. A few years later, Parsons ACSA and Binational Softwood Lumber Council ran the second Timber in the City competition, this time with a site at Essex Crossing, with a focus also on affordable housing. Alan Bruton served as the conference chair, bringing together Susan Jones, Tanya Luthi, Jeff McClellan, Tom Robinson, Amir Sharoki, and Jeff Spiritos to address the question, what's holding timber back? This is 2016. Right? The competition continued to gather great student interest, with the winning team from the University of Washington. Note again the focus on details, assembly systems, and prefabrication, and the embrace of the aesthetics of wood. 2 years later, we ran the third version with a site just near the Queensboro Bridge, expanding the focus to emphasize material health, informed by the work of the Parsons Healthy Materials Lab. I organized that year's competition and conference that preceded it, including presentations by Andrew, Tom Chung, Michelle Roloffs, Bill Browning, Merritt Buchholz, Allison Mears, David Linehan, Annie Perkins, and Todd Snap. Todd presented then the recently completed research on River Beach Tower, currently featured in the exhibition. And it's important to note that it wasn't just the demonstration of the use of mass timber for high-rise construction, but what I found really interesting about the project was that it was using assembly and construction rather than a substitute model for framing systems from steel and concrete. But here it's actually the very intricate details of timber that were driving the form of the tower itself. In fact, that this was a change in the maturation of the way in which to think about mass timber, linking then the shape of the tower to the facade, to its assembly, to its timber joints as the possibilities for the formal development. The Best Students projects explored similar tectonic opportunities of mass timber, while addressing the challenges of building adjacent to the bridge. However, students didn't do as well to address the issues of health or the broader regenerative of biophilic issues that were embedded in the project. This point is critical as issues that I want to raise here and moving forward. With little over 10 years old, these competitions now feel slightly missing of a key piece, namely the change in the way in which we conceptualize and understand materials that Alan has so eloquently spoken about. While detailing, assembly, and using new mass timber tectonics, these competitions did not fully address where the timber came from, how it was harvested and processed, what the health consequences of the full material assembly are, and how it would be disassembled and where it would go after use. 12 years ago, the understanding of the role of embodied or upfront carbon was not as central to the discussion as it is now, nor did the competitions challenge students and faculty to fundamentally change their conceptions of the role of the architect, to go from specifier of pre-made and prepackaged materials, including mass timber, to ones who can embrace, explore, and represent the full life cycle of materials to transform the way in which buildings operate dynamically as part of regenerative ecological global systems. As an aside, you can find all of the materials from these early competitions here. ASCSA has continued to run subsequent timber in the city competitions independent from Parsons, but notably without the important, from my perspective, conference gatherings to set the stage and set the information for making substantial change. I'm going to quickly rehearse in a slightly graphically different version from what Alan did to be able to argue for why this concept, this conceptual framing of the architect that needs to change is so critical. One is looking very clearly at the amount of CO2 equivalent. And our current policies, as Alan has mentioned, are not sufficient. Targets are not going to be met. Currently, we need to reduce by 65% by 2030 to 2024. This demands radical change. And while the emissions dropped during the global pandemic, they've kicked back up again. Meaning less time and need to accelerate change, right? Buildings are 39%, increasingly data is showing closer to 42% CO2. The emphasis has been historically on operational, not embodied carbon. About 50-50 of a new building is between operational and embodied. A high efficient building clearly starts pushing that far more into embodied. And the key question is the issue of time. That is the time that we need to be able to address now is the embodied carbon. The operational can be addressed later. Question then is the amount of construction and what we're going to build it out of. If we look at new construction over the next 50 years, we're effectively until 2060, we're looking at billions and millions of square feet, effectively 2.5 trillion square feet of building around the globe. They're going to need to be built. This cannot be done entirely through renovations. We're going to need to build new buildings. Right. Simultaneously, while embodied carbon and climate change are critical issues, they're only one measure of humans' impact on our capacity to exist within the limitations of the planet. as mapped by the now 9 planetary boundaries, a measure used by the Stockholm Resilience Center to demonstrate areas including biodiversity, water, chemical loading, ozone depletion, aerosol loading, ocean acidification, land change, and biochemical flows. As of last year, human inhabitation, we are now exceeding 6 of those 9 boundaries. What does this mean for the constructed environment and the practice of architecture? I think it's an imperative to move beyond the material and aesthetics and cultural values of global modernism, including utilizing timber under this very framework. Like simply substituting timber won't be sufficient. Need to move to that of a biogenic and geogenic materials that support renewable and regenerative cycles. On a formal level, this means moving from thinness to mass, thick, multivalent, singular, regenerative material systems that exploit a gradient between interior and exterior, as opposed to an interior and exterior. A year ago, my partners and I, recognizing a gap in accessible information to students, architects, clients, and builders, published this book, right? A follow-up to Manual of Section. It's a rethinking of the material basis of buildings, demonstrating a new paradigm for architecture and an outgrowth of our frustration with a consumerist understanding materials informing design practices and built into many of the digital modeling softwares. 9 chapters based on viable materials, and a final chapter on reuse, critically important. They showcase through 55 houses, small houses, built around the world that have already been realized to explore that the material and formal opportunities not only exist, but can be deployed and illustrated and examined through section. Of the biogenic materials, it's also important to note the time and the time pressures previously mentioned. Different growth cycles exist for these photosynthesized plants. Interestingly, while trees take 30 years, current agricultural crops such as straw and hemp operate annually, if not biannually. And this time question of where we're going to get our resources is tied exactly to the time question of the embodied carbon upfront for the operational over time. I'll show, in general, all the chapters follow the same framework, introducing the material, describing the rough approximate sequestered carbon, and then providing, and this is key for the educational framework, a clear diagram that's circular so that students and others can understand not only how the material was grown, but also the construction cycles and the relationship between growth cycles and construction cycles as part of the changing way of going to a circular way of thinking as opposed to a linear extractive waste linear process. Right? Wood framing, we also want to put into each of these chapters how it goes from the plant-based system into the products and how that products drives a way of thinking about construction. Mass timber in many ways is the poster child for the plant-based materials, and it's an exceptional material and has a storied history of architecture. I'm not dismissing this at all. It is no doubt better than concrete and steel, but it does have some important limitations. One is the growth cycle, and the second is the loss within the removal of the tree, disrupting the carbon in soil, significantly offsetting some of the carbon sequestering benefits of mass timber. This goes to forestry practices, understanding the broader cycles of forestry practice, not simply saying wood is the answer. Right? While certainly requiring much lower energy processing than industrialized extractive materials such as concrete and steel, a great deal of mass timber systems rely upon also adhesive. And so we have to be really careful about what the adhesive systems are and how they play into questions of disassembly. And this is in part why we find Dow laminated timber especially compelling, because it doesn't rely upon adhesives. We showed multiple housing projects, but we're interested in the houses that learned from the material to inform the form, such as Jennifer Bonner's house gables, where the very shape of the house is driven by the use of the CLT, rather than a substitution model of replacing one thing for another, but it looks like the previous material that you substituted for. Or in this case, 2 layers of CLT producing an enigmatic enclosure, a double skin system that actually doesn't rely on insulation for its thermal capacity. It uses the air between the double skins of CLT. Now, in this case, we're also calculating from the house the amount of sequestered carbon, looking carefully at where that is. And then after working on that book for 4 years, took 4 years of research to be able to pull it together, we were interested in designing our own projects, and I'll show one of them here, each looking at the kind of opportunities that come from bio-based building materials. In this case, we're interested in using the CLT blank, the very long and thin blanks, but how could it generate a form for a very tall house? So we're using 10-foot by 50-foot minimally tooled CLT blanks, where at the rear of the house, they go straight up, housing the stair core, and at the front, they taper to produce the iconic A-frame, creating basically a super tall house in the sky or in the forest that you can see the sky and see the tree canopy, and on the inside really exploit the qualities of the wood. In part, trying to figure out a building system that could use as much wood as possible from insulation to interior to the materials of the finish. One of the critiques of the building is why houses? And there's no question that the issue of housing leads to land use practices that we need to move away from. On the other hand, houses are a space for innovation, space for being able to testing and verifying things. It's also the place of huge waste in our current construction industry. Most houses are demolished after 61 years, and the total amount of carbon used to build North American houses exceeds the annual carbon of many countries, including Finland, Sweden, and Denmark. The other issue to note is that current contemporary houses are really big. They used to be 1,000 square feet. They're now 2,500 square feet. So all the houses in the book were much smaller, arguing that you can't just look at counting carbon. You actually have to look at material resources as critical to the project. But if you drill into the nature of the wall, and this goes to the argument about what the materials can do to be able to change the way in which we think about architectural practice, most contemporary residential projects are made from a sandwich whose only visible presence is paint and vinyl siding that is made of multiple cheap, lightweight, thin, single-performing, hygienic, sterilized layers with a strict binary between exterior and interior. We're interested in actually pursuing something very different. How can we radically rethink through plant-based buildings, monomaterials, thick, healthy, regenerative, where the thickness is actually embraced in part because of its architectural properties. It's also because of its thermal. It's also because of its carbon sequestering capacities. In this case, I'll end by looking at the complementary materials in addition to timber that one needs to look at to be able to address the earlier question, the questions that Alan's raised about how do we get to a sustainable regenerative practice. And I'm going to argue that straw is one of the key materials, and in part because it's a ubiquitous agricultural waste material. You don't have to displace any farm food crops to use it. Currently, there is an annual waste of straw after the kernels of food are taken away that is equivalent to 8% of all annual carbon emissions. 8% is wasted in some form. This is sitting there. It's low-hanging fruit to turn into building materials and has been used in building materials throughout cultures. Argument here, and this is put in the book, is that we need to take advantage of straw. How do we actually look at this as complementary, either as a roofing material or even as an insulation and structural material to augment our building practices, demonstrating it through built projects that use jumbo bales, in this case, Atelier Schmidt's Garris Pavilion, so that the zigguratting nature of the strong jumbo bales produces an incredible interior space and a super thick wall and sequesters a huge amount of carbon, 84,000 kilograms of CO2. Recent projects by the same office looking at the combination of hybrid of mass timber and straw to be able to produce monolithic prefabricated cassette walls for speed of construction. This is not returning to original form of building out of straw. It's actually using new technology to advance how we're going to build at speed and at scale and at size. A multi-story housing project being completed just this year, timber and straw. Right? This is an area that needs more work to accelerate, to take advantage of the waste material, but it's part of a broader framework of reimagining what we need to do to be able to get to not only zero, but get to a truly regenerative practice, coupling mass timber with urban forms, with architectural forms, with a change in the way in which we conceptualize architecture. So in the end, I'll end by showing a brief summary of recent research by LTL architects, working in collaboration with graduate students, many of which are at Princeton, as a way of opening up a discussion, arguing for an embrace of diverse palette of biogenic materials, of which timber is indeed part, but not the only regenerative material that we need to quickly embrace to transform how we inhabit this earth. Thank you.
Fred, we have you. There you are. You're going to overlook David's shoulder, I'm afraid. I don't know exactly how you feel like you're going to interact with this simulacrum of Fred there, but let me introduce Fred Bernstein, who many of you know and read all over the place. I counted on his website the number of publications, mostly architectural, in which he's published, and I think I counted 67. I don't know how accurate that is, but it is many, many. But I think most of us are most familiar when we open the New York Times or, well, the webpage. I still open the paper. When some famous architect has died, and Fred is almost always eulogized in the obituary. So he has an admirable and intelligent way of summarizing the architectural meaning as well as the content of people's careers. But we know that more recently, Fred has been particularly obsessed with the question of embodied carbon. And so that's why we invited him to be the commentator today. So Fred, I'm going to just let you take over and ask a few questions. And if the technology doesn't work, fine, I will intervene or, translate to those present. But knock wood, so to speak. Fred, take it away.
Thank you. Before I do anything else, I want to thank Carol Willis, who's one of the hardest working people I know, for organizing the semester of carbon. And I also want to thank you, Carol, for using the phrase upfront carbon. I'm not sure who coined the phrase. It may have been the journalist Lloyd Alter, but it's a wonderful phrase that we should all try to use, because embodied carbon makes you think the carbon is somehow embodied in the building, whereas in fact, it's up there in the atmosphere, and it's in the atmosphere before the building has even opened. It's a done deal. It's a fait accompli. Whereas the carbon savings that we always talk about, for example, from sequestration, are somewhat speculative. The tree has to get planted, it has to grow for a number of years, and so on. So upfront carbon is a terrific phrase. I also am honored to be on the stage, such as it is, with David and Alan. I've been aware of Alan and his innate love of wood for almost 20 years. I've written about several of Alan and Lisa's projects for the New York Times, and one was almost 20 years ago. And I'm aware of David, of course, because if you're interested in upfront carbon, you can't not be. When I did a story for Architectural Record about how architecture schools were revamping their curricula to account for upfront or embodied carbon, I don't think there was anyone who was doing more than David was doing at Parsons. And also, he's tired of hearing me say this, but the book he worked on, the Manual of Biogenic House Sections, is a complete triumph. I have several copies. I sometimes give them away as gifts. It's an amazing book. So I have a few questions for both of you. The first question, and this is an attempt to get you guys talking some more. Are there any ways in which your approaches diverge? Are you exactly on the same page? And if you are, we can move on. But I'm wondering if either of you has any thoughts about the other's approach to upfront carbon? Anything you would question or even describe differently? Silence.
Wow, you're really putting us on the spot. Do you want to start? No.
I'm not looking for trouble. I just want to know if you're exactly in sync.
Can you hear us, me?
I can hear fine if you're asking me.
Yeah, I am. And I hope you're feeling better. It's sad you're not here with us, but you actually are. So I'll start.
I'm here really big.
I'll start tentatively. I'm not going to describe differences. I think there were differences in how we were talking about the same topic.
Mhm.
I mean, David and I have been talking about these topics for quite a while and also working in parallel. The work of my lab in Bauhaus Earth in Berlin right now is doing exactly the work that you see in the biogenic section manual, which is looking at, say, polluted culture. So peatlands that have been drained, and now there are programs to re-wet them and to try to use as a means to generate a redistributive economy rather than a sort of hegemonic central one, to empower farmers and different landowners, to encourage them to re-wet peatlands, to find different uses for reeds, grasses, tifa grasses, etc., like straw. And I so embraced what David is talking about in those cases. I just focused on timber because I felt it was a little bit of the topic relating to current practices around timber.
Absolutely.
I guess the one last thing I'd say is, I think what I hope we can do in a discussion today is extend beyond the technical material practice and all of its performance benefits, and really start to look at the impacts and benefits to bigger systems, economic systems, people who might be enfranchised by practice. So that's not really a comment that David's missing that, but I hope that together we can talk about those things. And the same goes for ecosystemic benefits. So I think that's an important piece. But I don't know. I admire David so much. I would say that I follow his lead.
Oh, great.
Let me see if this is, I think one of the things that I would foreground, Alan, in your work, which I think is absolutely critical, is how does one represent the questions that seem unconceivable? In other words, questions of time, questions of sequence, questions of systems that now you're trying to translate into a two-dimensional page that conveys multiple layers. And I think this is what your office does extraordinarily well through the complexities of axonometrics, coupled with graphs that then build over time and then are built into lectures. So I think that the choice of representation is something that I think is really essential, because part of what we're arguing, and you argue to clients, is how do you convey something in a short time frame of not only what's possible, but the complexity of time frames and time horizons and cycles that don't lend themselves to traditional forms of architectural representation, or you have to use architectural forms of representation in a highly scripted manner to be able to make sure they're not just read purely as issues of form. And that's where I think we've looked to your work, looked to the other people in the space, to how do you actually graphically represent something? Because the question of education isn't just for students, it's for a broader understanding of a cultural change, which is systemic, right? Not just to architects, but to clients, to investors, to builders, to contractors.
How you make the case to clients could be the subject of a whole other evening, I would say. So I know we're here under the auspices of the Skyscraper Museum, which is great, but do we need mass timber skyscrapers? Let me ask the question a little differently. If all we were thinking about was housing those 2.3 billion people who are coming along, or so we're told, and all we cared about was doing it in a way that resulted in the least possible carbon emissions, what density would we be looking for? We're certainly not looking for single family homes on quarter acres, but I'm not sure we're looking for skyscrapers either. I've seen many studies that suggest that the sweet spot is maybe 6 to 8 stories. I'm wondering how you both feel about that.
I mean, I would answer the question not with a answer that's definitive, because I think it changes per location, changes by geography, changes by climate, changes by resource, changes by soil, changes by all the whole systems that you're building it into. So does it make more sense ecologically and from a standpoint of both calculation of carbon, but the broader 9 planetary boundaries, to build X story in New York may be of completely, and I suspect is a totally different answer than if you were to build it in New Mexico, then you would build it in Mexico, than if you build it in South America. Each area is going to have a completely different answer, but the question is, how do you study the broader systems into which that answer needs to be framed, as opposed to feeling as though there's a perfect solution. So I think this is what the complexity of the project is. It also leads with a question like, how do you frame those? How do you explore it? How do you research it to get to that very question that may in New York be much taller? I suspect it would be, because the existing infrastructure that may enable that, than a place that doesn't have that infrastructure, and those infrastructural costs are actually born into the challenge of gathering that number of people in a smaller point of area.
What if you were starting on a tabula rasa? So was it New York or New Mexico? It was.
We don't have one. There is no such thing. That is a modernist concept, and a problem has come from the very idea that we thought we had tabula rasas.
New world. I guess I'd give maybe a more biased answer to that question, although I totally agree with David's framing of the point. I think it really comes on either the question of sprawl and low density, morphologically distributed and dispersed building, the perfect American export. And the other extreme is the tall building, which goes to great lengths to use a material in ways that it probably doesn't have the inherent properties to reach those kinds of heights. So I guess there's a tipping point, just like we're facing a tipping point because of time. Where do we put our resources right now, given the fact that we have a rapidly closing window to rectify the damage that we created through at least centuries of exploitation of resources? So I worry, frankly, and this is no disrespect to all my friends who make beautiful designs for tall buildings, that there is a tipping point at some height, regardless of the cultural aspects of experience and the sort of contextual aspects, where wood is just working harder than it needs to work. We might question whether we need any really tall buildings at all, just like I question whether we really need suburban. To meet the demands of population growth and urbanization. So we're going to build tall buildings, or we're going to build dense cities. What does that density mean? What is a convivial answer? I think the answer experientially is highly personal. Some people love the densest parts of Tokyo, or Pudong in Shanghai. Other people would much prefer a small town of 2-3 stories. I like Barcelona, 8 stories. We will choose that. But I think within that, the resources that are at hand within the technological capacities that society has in the next 30 years need to be evaluated for their capacities at this point. Because I think we can dilly-dally a little bit too much if we try to achieve something which is beyond our reach, or if we simply replicate past practices of absolute voracious land consumption. So those are the 2 poles for me.
Thank you. I'm not sure how high we can go with mass timber, but I am pretty sure that we can't build skyscrapers out of straw or hemp or clay or mud. And I've been thinking about that, and maybe it's not a bug, maybe it's a feature. Maybe if we can't build skyscrapers out of those materials, we shouldn't be building skyscrapers. Because as David has pointed out, so convincingly in his work, we need to be using those materials, not just mass timber. So we should think about the limits of those materials as well, and maybe accept that we have to live with them. But we're here to talk about timber, so if you don't want to comment about that.
No.
Okay.
I want to note that I love the point that, and this is research that we're seeing in Europe a lot too, the point that David made about, the fat is the new kind of thing that we want. We want thick monomaterial systems because they're easier to produce, and they're also easier to dismantle and reuse and develop scenarios for that reuse. So I think I really embrace that. At the same time, buildings of height have a very different set of conditions than the single family 2- or 3-story house. you really have to have primary structure, secondary and tertiary structural systems, insulation systems. So there's a lot of places that we can deposit in tall buildings, whether they're 6 or 20 stories, earth bricks that are stabilized through chemistry, not through cementitious, the addition of cementitious material or firing, like we do with current brick making, with straw materials that are fireproofed and tested. I mean, there's a lot of really interesting research about all of these materials and how they fit into a complex assembly that is the multi-story dense building. So I don't think just because we can't build a 10-story building purely out of straw doesn't mean that straw could play an enormous role in urban building if we pursue the science around it.
Absolutely, absolutely. There are so many complicated questions that were raised tonight. Some of them really boggle the mind. If you're going to compare one material to another, there are so many factors that you need to consider. You really can't consider them all because it's endless. And somebody suggested a few weeks ago, I think maybe it was Michael Green, suggested that AI will be helpful in doing these calculations. So if you want to know which will be better for a building, steel or mass timber, and you really want to take every single thing into consideration, AI may be helpful. Does either of you have a feeling or a thought about that? A feeling, maybe, not even a thought.
I have a feeling and a nervous concern, bordering on paranoia over, the promise that we need to wait for something else to develop to save us from ourselves, is a really odd premise. And so one of the things that we've tried to do in the book, because the original premise was to do complex data calculations on every single one of the 55 houses. And we realized that that wasn't actually a useful challenge, that in fact, we wouldn't necessarily get accuracy, and accuracy wasn't the goal for that specific house. What was important was the conceptual understanding that in many ways is common sense.
Absolutely.
That one needs to work with materials that have a history we can look to, not that we need to replicate that history, but we can draw from that history what practices have worked, how have we built tall buildings prior to the Industrial Revolution, when are they useful, when are they possible to be, and where is it the augmenting of new technology, maybe not even AI, is necessary in order to deal with questions of scale. Because we're talking about questions of scale of how to build in the next 30, 40 years for an escalating population and to deal with the challenges that have to be dealt with at scale, where I think AI may be super helpful because of issues of speed, but not necessarily in the capacity to be able to provide an answer.
Common sense is very important. And what goes along with common sense is estimation. One of the reasons some architects give for not considering embodied energy is that it's too hard to calculate. And it is very hard to calculate, but you don't have to calculate it to 6 decimal points. Common sense is important. For example, Norman Foster is building a 1,400-foot tower on Park Avenue, 270 Park, for JP Morgan Chase. It's one of the most extravagant buildings I've ever seen, and they're calling it net zero. And no, it's not. And I don't have to do any calculations to know that it's not.
So I think this idea of learning instincts about impact are really important. That's one of the topics in one of our chapters in our carbon book, which is really trying to generate, obviously understanding how life cycle assessment works, but also understanding the biases that are in the databases that are applied to life cycle assessment, the black box programs we use on our plugins for Revit. These are all dangerous secrets that we need to learn more about. And the way to do that is to really make some good common sense responses. But I do want to mention AI, because I think that I'm a pretty much of a Luddite when it comes to this stuff, but we're working with Achim Menges and the Institute for Computational Design and Construction in Stuttgart, Bauhaus Earth, partnering, and we're looking at forest sources, and they're looking at different robotic techniques to do them. And we're using tomography to analyze timber, LiDAR to analyze timber stands, so that we can actually start to look at without cutting trees down, we can start to look at the properties and structural performance capacities of that wood. And then that creates this huge amount of data, which can be processed through AI potentially to develop really good solutions for the use of that particular material in that particular ecosystem. So, to me, I'm scared of big data, but I do think the processing of enormous amounts of really valuable information, if coded properly, might deliver some really good ecosystemically more stable solutions in building. I'm holding out hope.
Fred, wrapping up as we, come to the end of our more than an hour. Fred, last question or last thoughts, or David or Alan as well.
Yeah, so several times recently, developers have tried to convince me that their buildings were not just net zero or carbon neutral, but they were actually, let's say, climate positive. The construction of these buildings would result in there being less carbon in the atmosphere than there was before. And it's very hard to believe, and I don't think the numbers hold up. But this is especially for Alan. Are you saying that overall buildings can remove more carbon from the atmosphere than they cost to be emitted?
No,
I'm
not
glad.
at all. I'm saying that
Okay.
buildings, in concert with the incentives that building demand create on forests, could actually pay for some of afforestation where it's appropriate, forest restoration, strengthen forest carbon sinks, and then use a combination of forest carbon sequestration, building storage, substitution effects and benefits, and also salvage to really start to create an economy which draws down carbon to some degree. But it's not buildings. That's a mistake we always make as builders, that the building is the system boundary or the site is the system boundary. The system is global, and we have to manage how those exchanges happen. But one building will not ever be carbon positive.
Okay,
but
very
the
well
system,
said, and I'm really glad I asked the question. And I think, Carol, I think that's it for me.
David,
you, Fred.
a last thought.
The last thought I would have is this is a fantastic conversation because we're not beginning with form and then saying, oh, what's it made out of? But it's the exact opposite. Well, not even opposites. What's the material? Where does it come from? What are the consequences? And what's its possibility for informing how we inhabit? And that change, going to the question of education, is night and day from a dozen years ago, right? And it's also substantially critical to be able to make the changes we're needing because they are material based, and it's a practice that is material based, which is why the embrace of the unknown of unknown materials gives the capacity to look back to where things came and to look forward to unknown possibilities that puts the whole discipline of architecture, building construction in a completely different, I think, positive and generative way of thinking about its practices.
Here, here.
Well, you already are thanking them, but let's thank architects and educators as well as journalists for getting the word out farther about these really important ideas. So thank you, Alan, David, Fred, for a wonderful conversation. Tall mass timber buildings. You can find the whole list on our website, and we still have, and I'll show you the ones that are coming up in July, more topics to cover. You can watch the previous lectures, including Michael Green talking about his buildings in Vancouver and everywhere, and Susan Jones. And see next week, next Tuesday, Andrew Waugh, UK-based, London-based mass timber advocate who is one of the kind of earliest fathers of the movement and good friends, chums with our speakers tonight. Certainly a great influence on the adoption of cross-laminated timber and mass timber in North America, because Andrew built the first 9-story, that is the definition of tall in the survey of tall timber, 9-story all wood building in London back in 2009. So more than a decade ago. And Andrew will be speaking at the Skyscraper Museum. So we invite you there next Tuesday night. SOM's engineers will be speaking in the series that is the last of our July lectures, which is called Height and Hybrids, and Benton Johnson from the Chicago office, along with Alejandro Fernandez and from Thornton Tomasetti in Chicago, and Daniel Safarek, who is a Council on Tall Buildings Urban Habitat editor and author of their Tall Timber series, will be speaking along with Eric Karsh, who is a longtime advocate of mass timber and a structural engineer who worked with Michael Green and practices on his own in Vancouver. So pretty much everybody who has been in the series so far stands at the beginning in the intellectual commitment and investigation and research into timber, but then also the implementation in their own work and in spreading the word. So this series, we hope, fleshes out some of that, a little bit more than a decade or a dozen years worth of history in North America, and then some of the precedents with Andrew Waugh in London, the UK, but he'll also talk about the European context.